Welcome back to the course on memory device technology for AI/ML computing. I am your instructor Dr. Shubhadeep from Electrical Engineering at IIT Hyderabad. Let us have a quick recap of what we were studying the last time. We saw how the memory hierarchy, which takes the form of a pyramidal structure, is continuously evolving because of two primary factors. The first factor is the evolution of computing needs, which are getting complex by the day. The second important factor was that now we have access to growing number of new kinds of memory devices and also storage devices. So as we were seeing in the 1980s, we had access only to SRAM and DRAM. So the memory hierarchy was relatively simple. You had your CPU subsystem along with its caches, which had SRAMs, and also the next element of the memory hierarchy was your main memory consisting of DRAM. This kind of system was very slow because the next storage element in this entire chain was your magnetic disks, which are essentially sequential in nature. So in 1980s, the SSD or the flash memory or the flash cell was discovered at Toshiba, and as a result, after a few decades, solid state drives became very common and they could fill up a big chunk of the missing hole in the memory hierarchy. Nonetheless, still there exists a big gap between your main memory consisting of DRAMs and your SSD, which consists of flashes. Therefore, people are trying to look at storage class memories which can blur the lines or blur the functionality between main memory and main storage. So this is why storage class memories are seen to be futuristic devices which will fill the missing gap between DRAM and NAND flash. Okay, with this we go to the last part of our module, our first module. And here, if you remember, few classes ago, we saw that there were 6 important concepts that we need to be really strong about to appreciate what is memory device technology, especially from a hardware perspective, and how different things are organized in the memory hierarchy pyramid. So I know you can go back and see the video again, but for the interest of everybody, and because these are concepts that we will keep using, it might be worthwhile to quickly recap them. The first was latency versus capacity, and that was the rationale for having the memory hierarchy in a pyramidal structure. As you know, when you move down in the memory hierarchy, the amount of the capacity or the bit density grows, the bit density becomes more, the capacity grows, but also you suffer in latency. What was on-chip versus off-chip memory? All you need to remember is on-chip and off-chip is with respect to the CPU subsystem. So we had on-chip memory, which is generally consisting of caches, versus off-chip, where you use devices which is not really compatible with transistor technology. What was the importance of on-chip versus off-chip? It was again the trade-off between latency and capacity. The third thing that we looked at very carefully was memory versus storage. Memory was for immediate short-term needs, for frequent updates to the CPU, and therefore it required you to have very low latency, albeit low capacity, whereas storage was more for preservation and archiving of data. Volatility versus non-volatility was the fourth point, where we saw, where we tried to examine if the state of the memory is preserved after the main power supply to the memory is switched off. And we saw volatile devices, that is not the case. The device cannot remember once power is switched off, whereas in non-volatile devices, even after power is switched off, at least for a minimum of 10 years, you want to remember or hold on to the data. The fifth point was essentially how the memory arrays or the memory cells will be accessed. We discussed about random versus sequential access. In random access, you can at will pick out any row or column of the memory array, but in sequential access, you have to go one after the other. And the sixth important distinction was static versus dynamic random access memory. Remember, both static and dynamic random access memories are essentially volatile memories, but dynamic random access memories, as we will soon see, require continuous refreshing to hold on to the data because they are consisting of just one transistor and a capacitor, and as you know, capacitor leaks. So with this very quick recap, let us now go back to our memory hierarchy and try to draw the boundaries where you will see on-chip versus off-chip memory. So first, let us recall the essence of memory hierarchy. As you know, right at the top is your logic or your CPU. Below are your elements. As you go down in the memory hierarchy, you see that the access times increases or the speed reduces, but capacity, which is indicated by the, you can say, base of the triangle, also increases. So where do you think, I want all of you to pause and think what would be the boundary? Where should I draw a boundary between on-chip versus off-chip memory? So if you have been following this course well along, you may know that all the caches, whether it was L1, L2 and L3 caches, were made up of the same transistors, 6T transistors, which constitutes of the CPU also, or the logic element also. So it is but natural to expect, and this is what happens in nearly all systems, that the on-chip memory is restricted to the SRAM cells or the cache memory. So from CPU onwards to the L3 cache is what is generally a part of on-chip memory. The main memory, which consists of DRAM cells, is the first layer of off-chip memory. And although I might have already given you a hint why that is the case, I want you to take a moment, pause and think, why can't we include something like DRAM technology into on-chip as well? There is a clear advantage in doing so. The advantage is in latency. You would also want your main memory to function with very low latency, right? However, it is very difficult to integrate your 1T, 1C arrays or 1T, 1C memory or DRAM memory into the same chip as your CPU. And the answer why it is so difficult is very simple. It is regarding process technology. You have to appreciate that when we make these nanofabrication facilities for designing and fabricating certain kind of transistors, they are a very specialized center. So it does not make a lot of sense to diversify them into trying to make both transistors and capacitors. As we will see, making these capacitors in the DRAM is a very specialized technology in itself. And therefore, it makes sense to do them separately in two different foundries and then integrate them off-chip. Then is your storage class memories, which I have kept in a different color to indicate that they will be upcoming in the future, and your primary storage, which consists of NAND flash, which is also off-chip compared to even main memory. In the second module, when we look at some practical examples of memory hierarchy, the implementation of memory hierarchy in modern day mobile phones or modern day computers like my own computer, MacBook, you will see that the boundaries of on-chip memory and off-chip memory are not as fixed as I have tried to show in this slide. It is a more generic representation, and there are several exceptions, such as embedded DRAMs where the main memory is embedded into the on-chip of the logic subsystem also. And the advantage, as we discussed, clearly is got to do with latency. Okay, so once we have understood what is the boundary for on-chip versus off-chip memory, let us go to the next concept where we look at memory versus storage. So where do you think the boundary between memory versus storage will be? It is clear that the boundary has to be somewhere in between main memory and primary storage. But what would you classify storage class memories as? So the best way to look at the present situation without storage class memories is that there is a clear distinction between the main memory and the primary storage. However, as we have been discussing for quite some time, these emerging storage class memories can function both as memories and storage. Try to remember what were the essential features of memory. The essential feature of memory is that you need to have very fast access times. Read and write latencies need to be very small, whereas for storage, the essence is on preserving data, right? And the promise is that storage class memories will be able to do both. So in essence, as I have indicated through these arrows, the cache memories, L1, L2, L3 caches and the main memory can be classified as memory, which is tightly coupled to the CPU, whereas from primary storage onwards, which is made up of flash cells, and then your secondary and tertiary storage, which consists primarily of magnetic tapes, is for storage and data preservation. Another interesting distinction which we can immediately look at, where the lines are not really blurred and allied to the concept of memory and storage, is the concept of volatility. It is very clear that here the boundary is quite fixed. The expectation is that storage class memories and other storage class memories and other storage elements below going down in the hierarchy will be essentially non-volatile. It will be able to preserve data even when the power supply is switched off, whereas from main memory onwards, the focus is on fast access times, and since data is switching so frequently and it is very program specific or context specific, you may not really want them. There is not much need to preserve the data, so it can also be volatile. Okay, so once we have understood about memory, storage, volatility and non-volatility, and seen that the boundary for storage and memory is a bit blurred, but not so for volatility and non-volatility, let's go to the next important concept, which is about random versus sequential access. So if you have been paying close attention to the names of the device technology that is employed in each and every hierarchy, you will remember that the main memory is called DRAM. In the name itself, there is random access memory. What are the different kind of elements that was a part of storage class memory? Try to recall. They were resistive random access memory, magnetic random access memory. So the expectation even from storage class memories is that they will have fast access times, and therefore they have to be implemented in random access manner. Okay, and therefore the boundary between random access and sequential access is also very clear. Random access you would want to have till storage class memories, whereas as you know, your large primary storage, which is essentially consisting of NAND flashes, have block level sequential access. Now there is a small little bit of nitty-gritty detail which we will get into very soon. It is not necessary that flash cells are always sequential access. While NAND flashes are sequential access, you will see that NOR flash can have random access also. But NOR flashes are generally not used for high bit density storage. So this definition and this classification still holds. Just a small detail which we will discuss later on in detail. So final thing that we would like to discuss is what are the different storage, the individual memory or storage cells that are employed in different parts of the memory hierarchy, and this will be a good way to conclude our first module. So as we know, L1, L2 and L3 caches are consisting of 6 transistor based SRAM cells. The details of SRAM cells we will look very closely in the second half of week 2 and also week 3. I am not mentioning here the flip-flops and the latches which constitute of register technology, where the technology which is used to make registers in the CPU subsystem, because this is not something that is, the volume is not that large to be really addressed. So we will start our study from 60 SRAM cells which constitute of the L1, L2 and L3 caches. Please try to recall what was the element used in main memories. It was your DRAM cell, which consisted of just one transistor and one capacitor, and the memory was being stored where my laser pointer is at the storage node. Next, we want to discuss about primary storage, and here the key storage element was the flash cell, and the flash cell consisted of essentially one transistor, albeit the gate stack of the transistor was essentially modified so that you can store charges and remove charges, but this storage needs to be more or less permanent, at least up till 10 years. Next, we discuss storage class memories, which are not really there out in the market, but the promise is just 2 terminal storage class memories will be able to fulfill roles of both memory and storage. What do we notice when we go down in the hierarchy from caches to the main memory to the NAND flash and now emerging eNVMs? What we see essentially is the size of the cell is reducing drastically. Whereas we had 6 transistors for SRAM, we had just 1 transistor and 1 capacitor for DRAM. NAND flash consisted of 1 transistor. This is established technology. Whereas eNVMs consist of just 2 terminal devices, not even 3 terminals. So what does this mean? As you go down in the memory hierarchy, you are trying to make the cell area smaller and smaller and improve bit density. But as we have been seeing in this course, nothing comes, there are no free lunches, it doesn't come free of cost. The cost is the increased latency. So I hope you understand that each device or memory technology is designed to fulfill a specific role within this large infrastructure. The final thing we want to discuss very briefly is about magnetic tapes, and we know magnetic tapes is not really solid state technology, so we will not discuss much about it, and we would also consider that it is now quite outdated. We don't use magnetic tapes other than for old time's sake, to remember old time's sake, or sometimes it is very useful in servers, in large data servers to archive data. But other than that, since it's not a solid state device and they have become pretty outdated, we will not discuss about magnetic tapes in this particular course. So let us conclude our module 1 with the important learnings, the key insights that we gained. The first insight we got, there has been a remarkable shift in the compute paradigms from logic-centric computing to data-centric computing, and all of this was supported due to the availability of big data. And what led to the availability of big data? It was these advances in memory and storage technology. The second important thing we saw was that there is a very important need to classify memory and create a hierarchical setup. We saw that the modern day computing, although is based on the von Neumann architecture, there have been lot of advances in the implementation of von Neumann architecture, but von Neumann architecture essentially is not able to support high intensity data driven computing. To supplement this, we discussed about the memory hierarchy, what are the important classifications, and the need to organize the memory hierarchy in a pyramidal fashion. Please recall, it was essentially the trade-off between capacity and latency. Third, we saw how the memory hierarchy is essentially evolving as time passes. This is due to the evolution of computing needs and the availability of newer device technologies for memory and storage. And finally, in today's class, we saw how these important classifications, the 6 important classifications, fit into the memory hierarchy pyramid and what are its important functions and what value it brings into the entire chain. This is a particular image which I am very fond of and pretty much encapsulates what is the need for memory hierarchy, and we would like to stop with this particular image. If you see the x and y axis, both are in log scale. The x axis is the integration density, which is in bits per millimeter squared. How many logical bits can you fill per millimeter square? And as you can see, there is a big range, 3 orders of magnitude, from 10 to the power of 7 to almost 10 to the power of 10. What is the y-axis? The y-axis is essentially access times. And the range of access times is even what you would say large. It is from hundreds of picoseconds to few milliseconds, right? Several orders of magnitude, almost 8 orders of magnitude difference. And this is the competition that we were continuously talking about between capacity in the x-axis and latency in the y-axis. And as you can see, in the bottom left corner, you have your SRAM and DRAM, which is essentially memories, which have a volatile nature. They have very low bit densities, but very fast access times. Therefore, they are tightly coupled to the CPU. On the right hand side, top corner, in green circles, you see non-volatile storage technologies such as NAND flash and magnetic tapes or HDDs. While they have very large bit densities, they suffer from low latencies. And this gives us the reason why we need to come up with new storage class memories, whether it is PC RAMs or RRAMs or MRAMs, which can fill this big gap between bit density and access time. And this is what storage class memories aim to do. So this is a good encapsulation of the memory hierarchy that we have been looking at very closely. Okay, with this, let's conclude. Hope to see you soon again.